Hi there, welcome to Kung Fu Physics, where we are solving practice physics GRE problems one at a time. The problem today I want to look at is number 6 off the 1996 exam. So the 1996 exam, number 6, it's going to look something like this. Sorry, there's a bit of a water drop there to the left of it, if you can see that, the diagram, but ignore it. Anyways, the problem looks like that. I think this will be one of the shorter videos if I can keep myself from rambling too much, because I think it is a very easy concept. I just briefly, before I started this up, looked at the website that tends to post physics GRE solutions, and their solution that's right there under the posting just seems more complicated to me than it needs to be. In my head, this is a pretty straightforward problem, really straightforward problem. It's a dynamics problem, and let's go right into it. Like I said, it shouldn't take too long. Alright, number 6. I usually glance at the answers. Glancing at the answers there, something that's most interesting is answer E. There is a 0 there. When I see something like that right off the bat, I am hoping I can either readily pick that answer or eliminate that answer pretty quick, because it's so different from the other ones. If I was really sharp, I would maybe be able to look at the other answers quick and realize that they are the same units, because, well, if I imagine mu as a coefficient of friction, unitless, sine of theta is unitless, right off the bat I wouldn't be able to eliminate anything off of units. But it would, have to be a quick scan of those answers. You can't waste too much time doing that, of course. And then you're on to the problem. Number 6. A block of mass m sliding down an incline at constant speed is initially at height h above the ground, as shown in the figure above. The coefficient of kinetic friction between the mass and the incline is mu. If the mass continues to slide down the incline at a constant speed, how much energy is dissipated by friction by the time the mass reaches the bottom of the incline? And I've always loved work energy problems because of their simplicity. And to me, in my head, what I'm constantly doing, even if I have to do several steps in it, is I'm just imagining the energy of the situation before, and then the energy of the situation afterwards. And whatever's in question. And I realize those are always the same because energy is conserved. I'm always setting those two quantities equal to each other. Now, there are times when something like a non-conservative force like friction is pulling energy out of the system, but the energy is still there. That energy has just been converted to useless friction, which is never going to be able to be used to do any work on anything, but the energy is still there. And so that's the important thing, and I only really have one equation for this that would look something like, I guess in this system, I would say the potential energy initial plus the kinetic energy initial equals potential energy final plus kinetic energy final plus any energy, I'm just going to call it E, and in my head what I'm seeing there is any energy lost to friction. Okay, so that's the energy that's taken out of the system. In other words, total energy initial has to equal total energy final, just by conservation of energy. The potential energy initial is going to be mgh. Now, if you read the problem carefully, and if you need to look at it again, when you're doing these, by all means, you're probably going to be looking at the problem a couple times for confirmation of what you think you know about the problem and how you think you're going to be working the problem. But the kinetic energy initial, we could just say this. I mean, this thing has a constant velocity, so we could just say it's 1/2 mv squared equals the potential energy final. And if we're saying this goes all the way to the bottom of this ramp, then you can see it's therefore horizontal to the very bottom part here. It's traveled vertically the whole distance h. So it went from the top to the bottom. So that's going to be 0, because if we're taking the reference point for our potential energy at the bottom of that ramp, that's going to be 0 plus, and then is this still here? It is. If you read the problem carefully, it's saying it's keeping a constant velocity, so there's still kinetic energy final, that's 1/2 mv squared, and then plus E. Now, I could get a little fancier with E if they asked me to find something different in the problem. I know that E is going to be the normal force of friction times the distance traveled down there. That's not necessarily to solve this problem, but I just want to put that in there as a reminder. For example, if they said, I don't know what else they could say, but I can imagine another problem where they could be looking for one of those two things perhaps. But this stuff all just goes away because you've got the exact same kinetic energy before and after. This is just a 0. You have mgh equals this, and what I am recognizing this as is the energy dissipated. I'm not even going to bother writing it out because my handwriting's terrible. The energy dissipated by the friction. And so all of this energy, mgh, has been converted to friction. I guess the only way that people would answer anything different on this problem than B is the answer that's jumping out at me, mgh, is maybe they're assuming the situation is more complicated than it is. Don't do that. Don't race into doing unnecessary calculations. Don't make any assumptions thinking, oh, well, this is what I always had to solve for in these types of problems. Certainly I'm going to start doing it, because then you're going to waste however many minutes of time you waste on that problem, and it's unnecessary. If then you have to go back and say, oh my gosh, it was that much more simpler, I just had to look at it this way. So this problem is a really great illustration about how simple some of the physics GRE problems really are. This is simple on several levels. It's simple because it's just a kind of a dynamics problem, freshman physics, classical mechanics, forces, friction type of stuff. Very easy that way. But hopefully you agree with me when we see that it's very easy to solve. You almost don't even have to write anything down. And you can almost just think of this one conceptually and do it all in your head. So easy problem today, and probably a couple more easy problems to follow. I sort of sort through them, and I try to put one out a day, and sometimes when I get behind, I sort of am going to be looking and grabbing some of the easier ones that I've stashed away when I'm in a hurry to do these, like today. So that's all. Study hard, and I'll see you next time.